Project final project. This is the project is automated design of a self-learning firewall for intelligent building management system. This is the outline of our presentation. First we'll talk about the motivation behind our problem and the problem statement. Then we'll give our model of the smart home. Then we'll talk about diffusible logics and how Spindle can work in that way, to solve this problem. So there will be examples on the conflicts in user policies, and there will be the solution, how to solve the conflicts, and then we'll give a description of our future work. Internet of Things. First of all, what is Internet of Things? Internet of Things is a network of physical objects in which objects have the capability to communicate over the network without human to human or human to computer interaction. However, security risks are bolstering with the emergence of this network, as it is allowing embedded network sensors and actuators or stretched everywhere to have access of all sort of sensitive things. An intelligent building or smart building or ambient environment is one of the part of the Internet of Things. Nowadays, the main aim of developing an intelligent building is to make it energy efficient. Task because of integration of various types of devices which are used by various vendors using diverse protocols, and they are made to talk in the same network, which are amplifying their vulnerabilities. So nowadays maximum of the intelligent building are used fixed schedule based, because it lessens the problems of users policies conflictions. So in the statistics, from the statistics we know that in smart building may have more than 30,000 rules. So if user interacted with this smart buildings environment, and if there is a environment for the user to monitor his environment using policies, because of the difference in the behavioral reasoning, there must have been some conflicts. So an attacker can easily take the advantage of these vulnerabilities due to the confliction in the policies. So nowadays the intelligent building management system are focusing more onto the resolution of these user conflicts, because fixed schedule based intelligent system generate extraordinary amount of data, and it's completely generate huge amount of wasted energy. So this is the architecture of our smart home. These are all the entities of sensors, and these are all the entities of actuators. Actually, there is an indirect relationship among these sensors and actuators, and there is a many-to-many relationship among the sensors and the actuators, which means that an actuator can take the data from many sensors, because it reduces the vulnerabilities that may occur from the malicious data. So an actuator, for measuring a component of the environment, there may be many sensors. That means two or more than two sensors can measure the temperature. So this reduces the possibilities of attack or error of the sensors, and there is a sync node that we call controller. The sensors will send the data to the controller, and after the analysis of the data, the controller will give the commands to the actuators, and there is the data servers intelligent enabled by various sensors and various data communicating devices. Today's intelligent building generated huge amount of data, so it is very needed to ensure the control of the access to this data, and develop a user management tool for the management of the data. This is our future plan of designing an extensible and distributed architecture for the control of the data and the management. So now we the actual scenario, the sensor will measure the environment components, and then it will send the data to the data server. And data server, there will be some applications, client application, which will work on this data, and it will updated the data according to its recent readings, and it will filter out the backdated data. And there is an access of this data server from the internet, but we will design a architecture where to access this data a user may need a token, and this token will be given during its registration. So because of the, using internet, we are planning to implement a firewall among between the internet and the controller. This firewall will be automated rule generator, and there will be some policies. The controller here will the data server, after a fixed time or after a trigger, the data server will send the recent data to the controller, and the controller will have policies given by the users or admins or managers, and analyzing the policies and analyzing the data, he will generate a command which will be given to the actuators, and the performance of actuators on the environment will have an impact that we have shown with the dotted line. That means if someone actuate the temperature actuator, which will switch off or switch on the cooler, it will have impact on the temperature. Suppose for switching on cooler, the temperature will decrease, and we have shown this decrease through this dotted line. So there will be another policies on how the data will be transmitted, and what will be the rate of this transmission, and what will be the rate of the sensing. From the related work, we have decided using data variance for measuring the transmission time. We know sensing that transmission of data takes double time than the sensing of data. So we will try to dynamically adjust this transmission speed according to the variance. So this is our smart home architecture, and this is a paper on the user interactions. I have already said that fixed schedule based intelligent system is easy to implement, but it causes a huge amount of wasted energy. So if we want to interact users, it will make the environment more comfortable for them, but it's really a challenging task, because there is a difference in their behaviors, and this variance in behaviors will cause the conflicts. So if we want to integrate our system with the interface that will help the users to give their policies according to the environment, and if he has the capability to control the environment of his room or of his environment, so we have to develop a user interface that will be able to resolve all the conflicts, and that will assist the users in giving his rules. So in this paper, actually, they have defined two type of agents, room agent and coordinator agents, and they are all the agents express their behavior through three types of rules. One is preference rules, that is controlled by the room agents, and other two is maintenance and emergency rules that are maintained by coordinator agents. First of all, I'll talk about the room agent. A room agent gives the preference rules. He has three types of rules. First of all, strict rules, defeasible rules, and the defeater rules. Strict rules is something that is inevitable. Suppose he explained that if it is more than 4 a.m. then it is afternoon, or if he said that if it is May or June it is summer. So this can be the strict rules. That means this is a truth, universal truth types of things. And then we will talk about the divisible rules. The divisible rules are like someone tell that if it is 4 a.m. it is afternoon and we have to switch off the light, and so after 4 p.m. they will switch off the light according to one room agent, and another room agent expressed that after before 5 p.m. there will be no turn off of lights. So one is between 4 p.m. to 5 p.m. one agent is telling that the switch that the light switch will be turned on, and another agent is telling that the light switch will be turned off. So these are the divisible rules. And one is defeater rules. The defeater rules helps to get a conclusion from the divisible rules. Suppose one rule said if there is no person, switch off the light. So it will help when the time is 4 p.m. to 5 p.m. This will tell if there is no person, just switch off the light. So these are the type of rules that can be provided by a room agent, and then the coordinator agent. The first task of the coordinator agent is giving maintenance rules. The maintenance rules tends to energy consuming, so it will try to use the energies in such a way that the system will be energy efficient. So when users will give the preference rules as to the coordinator agents, because the coordinator agents have to allocate resources to these room agents to activate his rules. So it's the coordinator agents who needs to allocate resources for the preference rules. So all the room agents send their preference rules to coordinator agent, and then he will select among them which will be allocated resources according to its maintenance rules. The maintenance rules is for energy consuming, and it will say, suppose if there is more than 30 kilojoule is used, switch off all the coolers. So at that time there will be no preference will be working, because coordinator agent is implying its own maintenance rules. And there is another type of rules, that is emergency rules. That emergency rules can be switch on all the lights during the fire attack. So the building is caught by fire, and so it switch on all the lights so all the occupants can see the way. So this is emergency rules, and there is a priority among these rules. The emergency rules is prior than maintenance rules. So when it is emergency, this rule must be executed. So also we can define this divisible logic with the superiority relationship. Suppose there is a two person in a room and they have given their policies, but person 1 has the superiority than the person 2. So the coordinator agent will do what the person 1 is saying, ignoring the person 2. So so this is a type of way how we can interact our users. But this still exists a problem, because you cannot conflict the resolution when you can resolve the conflicts when there are persons who has the same hierarchy, who are in the same level of the hierarchy. So in that case we have to solve the conflicts. So we are using spindle for solving our conflicts.
Hello everybody, this is Abdullah Farouk. I'm working in the same project there. So I will talk about how Spindle works. So this slide is about diffeasible logic programming with Spindle. Actually Ashutosh covered most of this, so I'm skipping this real quick. So what I am going through to the Spindle, that how the conclusion has been analyzed when we run the Spindle, the diffeasible reasoner, with the smart home environment. So how can we get the results? I mean, what do we know from the results? As we can see from here, when we get the result plus D, that means the query is definitely provable in the theory. And when minus D, that we have proved that Q is not definitely provable in the theory. And the plus D represents that Q is diffeasibly provable. So when there is superiority relation and we input it there and we find a query with plus D, that means we can prove it diffeasibly. So it is proved, and minus D means that it's not possible. So it's not definitely possible and it's not diffeasibly possible as well, provable, sorry. So this is the policies for a smart building. Exactly the policies are embedded here, the user interaction that Ashutosh has shown you just now. So we inputted this code directly with the Spindle. I'm just showing you real quick that how it works. Okay, so here is the Spindle diffeasible theory. Let me talk about the Spindle thing first. This has been developed by a research group in University of Victoria, University of Queensland. I'm sorry about that. That's in Australia. So this is open source, and I'm using it. This is the basic diffeasible one. So this is exactly what we have shown in this page. And we can see it here. The rules have been embedded. Actually, I wrote it in TextPad, and then it is embedded over there. So when I run the conclusion. This is generate conclusion. So as can be seen, that these are the results here. So in the results, what you can see, plus D, switch on cooler. That means it is diffeasibly provable that switch on the cooler A6 is switched on. So how is it possible? If you can see from the presentation slide once again, you can see the temperature A6 is 30 now at this moment. So there is a rule that says that when temperature is greater than where is that one? Temperature, yeah, temperature is greater than 28, that is temperature high. And when temperature high, that means switch on A6 cooler. But you can see this is diffeasible rule. I mean, this kind of sign is strict rule, this kind of sign is diffeasible rule. That's why you can find that, okay, switch on A6 cooler is on actually. So I just pointed out that with red sign that we can find that it is on. So what is the problem with this policy? The problem with this policy is that they never considered a heater, and they never talked about humidifier. So we try to input those in the same room. So what happened there if we do that? Okay, there are some logics over here. I mean, we inputted here A6 heater, switch on A6 heater, new type of heater, and we found the normal logic. When the cooler is on, switch heater will be off, something like that. And we said that when temperature is low, then the heater will be on. So there is a conflict. What is the conflict? If you think it carefully, when the temperature is high, that is now at this moment, then the cooler will be on. When the cooler will be on, it will reduce the temperature. So when it reduces the temperature, then it will go below the threshold. The threshold is here. I think it is 18 or something like that. 18, yeah. When temperature is then it will go below 18, and at the same time it will trigger the heater to on. So in the same room, A6 is the room number, the heater will be on and the cooler will be on at the same time. So I'm just saying it. So how will you believe me? So you have to believe me from the this thing. Let me open the modified theory. Here the heater heater stuff has been inputted. The heater rules, the rules for the heater has been inputted, and here also says that when the temperature gets low, the heater will be on. And here, no more superior relationship has been added. So let's run this thing. So when we run this thing, we will find that cooler is on, cooler is off, heater is on, heater is off. All are not diffeasibly provable. And we added another thing, humidifier. It says that when the humidity is less than 65%, then close the humidifier, and when it's less than 45%, it will be open the humidifier, I mean not closing the humidifier. So this is also another conflict, because what if, I mean, we inputted the humidity is 40%. So what will these two rules do? It will open and close, open and close. So this is a conflict. An attacker can easily take leverage from this one. So what we did over there, we ran it, and what we found that humidifier is closing, humidifier is not closing. That is not diffeasibly provable. That means it's not true. Both are not true. That means it's opening, it's closing and opening. And same thing happened with the cooler and heater. The heater is on, the cooler is on, the heater is off, the cooler is off. Everything is possible, everything is provable here. So this is a conflicting situation. So that is the main thing contribution of our work. So I mean, I just skipped one page here. So what kind of conflict over here? We found a paper. Actually, all the references here, I didn't put it here, but in the report you will find all the references. So first type of conflict is environment mutual conflict. What it does, heater and cooler can be turned off at the same time. Turn on and turn off. Execution conflict, humidifier turns on and off at the same time. Shadow conflict, humidifier gets confused. Which rules to be triggered? So these three type of conflicts are there. How we can prove that? With this. That means they are not provable. So how to solve this thing? We just added some superiority relation just exactly in this side at the end. What it says, we just assume that it is actually summer season. That means temperature is generally high, so the cooler will be on. So we give the cooler as priority. And another thing we did for the humidifier is when the humidity is below 45%, then it will be triggered, not the 65% thing. So when we do these things, we run it, and we found that you see plus D close minus close humidifier. That means what? It is diffeasibly provable that the humidifier is now open. You can see this red mark over there. And if you see for the cooler and heater, that means you find that it is diffeasibly provable that switch will be on for the cooler in that room, and it is diffeasibly provable that for the heater it must be switched off. So let me run that again for you from the spindle. So how we did that again? This is the final one. If you see the final one, here are the superiority relation I just told now. So when I run it, run generate conclusion. Yeah, this is the one I just showed you. You see here the cooler is on. We found it. And here the heater is not on. That means in the same room this kind of confliction is not happening. So this is actually our main contribution, that we have formulated how the conflicts can occur, and we solve some solution over there, and this is the whole thing is automated. So at the end I'm talking about the future research iteration. So what is possible over there? Model possible conflict. We will do the modeling of possible conflict space and proving that it is complete, because we found one paper what says that 5 type of conflict happen, but it's not proved that these are all the 5. So this is one of our future research direction. Another will be threat modeling with conflicting situation. We will do that. We will formalize the threat modeling. And the last one, the most important one, is the model checking and verification for the whole system for ensuring security. Me and Ashutosh both have read lots of paper on these 3 topics, and we believe that this is a very good and open research direction for both of us. Maybe I will go through maybe the threat modeling with conflict institution. After we'll go to model checking and verification, and we will extend the project maybe for a publication or something like that. So that's all for us for today. Thank you very much for having patience with us. Thank you. What can we use? Control the right.